solution in one beaker to solution in the other beaker proves by the migration of ions to the salt solution. We know that the flow of current is possible only if there is potential difference between the copper and zinc rods known as electrodes here. The potential associated with each electrode is known as electrode potential. What is an electrode potential? The potential associated with each electrode is known as electrode potential. If the concentration of each species taking part in electrode reactions is unity, if any gas appears in the electrode reaction, it is confined to 1 atmospheric pressure, and further reaction is carried out by 298 Kelvin. Then the potential of each electrode is said to be the standard electrode potential. By convention, the standard electrode potential E minus of hydrogen electrode is 0.00 volts. The electrode potential value for each electrode process is a measure of the relative tendency of the active species in a process to remain in oxidized/reduced form. The negative E minus means that the redox couple is stronger. Negative E minus means the redox couple is stronger reducing agent than the H plus H2 couple. Positive E plus EA positive electron means that the redox couple is a weaker reducing agent than the H plus and H2 couple. And the standard electrode potentials are very important, and we get a lot of the useful information from them. The values of standard electrode potentials for some selected electrode processes, reduction reactions, are given in table 7.1. We'll learn more about electrode reactions in 7 faster. Redox reactions form an important class of reactions in which oxidation and reduction occur simultaneously. Three-tier conceptualization, which is classical electronic and oxidation number. Classical electronic and oxidation number, which is usually available in the texts, has been presented in detail. Oxidation, reduction, oxidizing agent, oxidant, and reducing agent, reductant, have been viewed according to each conceptualization. Oxidation numbers are assigned in accordance with a consistent set of rules. Oxidation number and ion electron method both are useful means in writing equations for the redox reactions. Redox reactions are classified into 4 categories: combination, decomposition, displacement, and disproportionation. The concept of redox couple and electrode processes is introduced here. The redox reaction find wide The redox reactions find wide applications in the study of electrode processes and cells. extension in the beginning. Particular species. This and that species is present in all an indirect redox reaction is made to convert chemical energy into electrical energy. Luigi Galvani and Sanford cells are also known as galvanic or voltaic cells. Sign reaction with sign cathode positive due to consumption of electrons, negative due to release of electrons. The reaction is reduction in cathode, oxidation in anode. Movement of electrons is into the cell in cathode, out of the cell in anode. Redox reactions and electrode processes. In experiments corresponding to reaction, zinc plus copper gives rise to zinc 2 plus copper. Must be observed as zinc rod is dipped in copper sulfate solution. The redox reaction takes place during the reaction since zinc is oxidized to zinc ions and copper ions are reduced to metallic copper due to the direct transfer of electrons from zinc to copper. In this reaction, heat is also involved. Now we modify the experiment in such a manner that for the same redox reaction, transfer of electrons takes place indirectly. This necessitates the separation of zinc metal from copper sulfate solution. We take copper sulfate solution in a beaker and put a copper strip or rod in it. We also take zinc sulfate solution in another beaker and put a zinc rod or strip in it. Now reaction takes place in either of the beakers and at the interface of the metal and its salt solution in each beaker, both the reduced and oxidized forms of the same species are present. These represent the species in the reduction and oxidation half reactions. A redox couple is defined as having together the oxidized and reduced forms of a substance taking part in an oxidation or reduction half reactions. This is represented by separating the oxidized from the vertical line or slash representing an interface solid slash solution. For example, in this experiment, the two redox couples are separated as zinc Zn2 plus slash zinc and CO2 plus slash copper. In both cases, oxidized form is put before the reduced form. Now we put the beaker containing copper sulfate solution and the beaker containing zinc sulfate solution side by side. We connect solutions in two beakers by salt bridge, a U-tube containing a solution of potassium chloride or ammonium nitrate, usually solidified by boiling with agar-agar and later cooling to a jelly-like substance. This provides an electric contact between the two solutions without allowing them to mix. The zinc and copper rods are connected by metallic wire with the provision of an ammeter and a switch. The setup as shown in figure is known as Daniel's. When the switch is in off position, no reaction takes place in either of the beakers and no current flows through the metallic wire. As soon as the switch is in on position, we make the following observations. The transfer of electrons now does not take place directly from zinc to CO2 plus, but through the metallic wire connecting the two rods as is apparent from the arrow which indicates the flow of current. The electricity from solution in one beaker to solution in the other beaker flows from migration of ions through the salt bridge. We know that the flow of current is possible only if there is a potential difference between the copper and zinc rods known as electrodes. The potential associated with each electrode is known as electrode potential. If the concentration of each species taking part in the electrode reactions is unity in gas appears in the electrode reaction, it is confined to 1 atmosphere of pressure and further the reaction is carried out at 290 Kelvin, then the potential of each electrode is said to be the standard electrode potential. By convention, the standard electrode potential E of hydrogen electrode is 0.00 volts. The electrode potential value for each electrode process is a measure of the relative tendency of the active species in the process to remain in the oxidized/reduced form. A negative E means that the redox couple is stronger, reducing agent than H plus H2 couple. A positive E means that the redox couple is weaker, reducing agent than the H plus H couple. The setup daemon cell. Electrons produced with the anode due to oxidation of zinc travel through the external circuit to the cathode where these reduce the copper ions. The circuit is completed inside the cell and the migration of ions to the salt bridge. It may be noted that the direction of current is opposite to the direction of electron. It's always in electricity we will learn. The two half cells of galvanic cell are connected by a salt bridge. A salt bridge is an inverted U-tube with an electrolyte in a gel that is connected to two half cells of a voltaic cell. The salt bridge allows the flow of ions but prevents the mixing of different solutions. And it will allow direct reaction of the cell reactants. The half cells are connected externally so that an electric current flows the two half cell reactions. And they are as follows. Anode has zinc, which is zinc 2 plus N2 electron is given out. Oxidation half reaction, then cathode has CO2 plus with the 2 electrons are consumed, so it's 2 reduction half reaction. Net reaction, what takes place is zinc plus CO2 plus gives rise to zinc 2 plus C. Salt of anions towards anodic compartment and cations towards cathodic compartment. It is a glass having potassium chloride or ammonium chloride or ammonium nitrate in a gelatin form. The gelatin allows ionic movement but prevents any kind of mixing. In case of potassium chloride or ammonium nitrate, the ionic mobilities of cations and anions are same. Potassium chloride and ammonium nitrates, the mobility of cations and anions are the same. Functions of a salt bridge. The common functions are a salt bridge acts as an electrical contact between the two half cells. It prevents mechanical flow of solution, but it provides free path for the migration of ions to maintain an electric current through the electrolyte solution. It prevents the accumulation of charges. A salt bridge helps in maintaining the charge balance in two half cells. A salt bridge minimizes/eliminates the liquid junction potential. Note, if the salt bridge is removed, the EMF of the cell drops to zero. Electromagnetic function of the cell drops to zero. Electrode potential and its measurements. This is good. This is good. Electrode potential and its measurements. A cell EMF is a measure of the driving force of a cell reaction. This reaction occurs in the cell as separate half reactions, an oxidation half reaction and a reduction half reaction. The general forms of these half reactions are reduced species, which is oxidized species plus the number of electrons given out, that's oxidation anode, reduction cathode. Oxidized species, reduced species, reduction cathode. E cell equals to oxidization potential plus reduction potential. Oxidization potential plus reduction potential. In present estimation, the electrode potentials are measured in terms of reduction electrode potential. Therefore, E cell equals to reduction potential of reduced species minus reduction potential of oxidized species. you can construct a table of reduction potential, you will have a list of strengths of oxidizing agents. In addition to having a way of calculating cell yield, you can look at an oxidation halves reaction as the reverse of a corresponding reduction half reaction. The oxidation potential for an oxidation half reaction equals to the negative of the reduction potential for the reverse half reaction, which is a reduction. Oxidation potential of for a half reaction equals to reduction potential for the reverse half reaction. So this means that in practice you need to tabulate only oxidation potential or reduction potentials. The choice by convention is to tabulate reduction potentials. We call these electrode potentials and we denote them by the symbol E without the subscript cell as in E cell. Without it. Zn is slash Zn plus aqueous double slash of Cu2 plus aqueous slash Cux. The half reaction R. Zns gives rise to Zn2 plus 2e electrons by E minus given off. The Cu2 plus of 2e minus is accepted, gives rise to Ce. The first half reaction is an oxidation. If you write Ezn for the electrode potential corresponding to the reduction half reaction, Zn2 plus gives rise to Zn, then minus Ezn is the potential for the oxidation half reaction. Zn is gives rise to Zn2 plus 2e minus. The copper half reaction is a reduction. Write Ecu for the electrode potential. The cell EMF is the sum of potentials for the reduction and oxidation half reactions. For the cell we have been describing, the EMF is the sum of reduction potential, electrode potential for the copper half cell, and the oxidation potential negative of the electrode potential for the zinc. That was for this study live session. See you soon in another study live session. Will come yeah. So till then, happy studying. Bye bye.